It's a pleasure and honor for me to be here at this conference, and I would talk about convergence of multidimensional Mellin-Barnes integral. Exactly, I would talk about convergence of integrals which represent algebraic functions. We start with We start with case of one equation. In 1921, Mellin obtained the integral of Mellin-Barnes, which represent the solution of algebraic equation form 1. This integral has non-empty convergence domain, and later this result was improved by Antipova, and she obtained conditions for this domain. Okay, let's start. Okay, we have equation phi1. We call branch y of x of solution 1 near x equals 0, selected by the condition y in 0 equal 1, principal solution to equation 1. Denote vectors alpha and beta, these vectors of exponents in these equations. And beta is a vector q minus alpha. Let y is be a principal solution of equation 1, and for any mu greater than 0, the function y can be represented by the following Mellin-Barnes integral. The vector r is taken from simplex U. The domain of this integral in variables theta, which equal arguments of x, is defined by the inequalities this. Okay, this theorem is proved by direct and inverse Mellin transform. Mellin transform is the transform which transform of this form. And this inverse Mellin transform. But if we simply apply direct Mellin transform and then inverse Mellin transform, we don't show that the function is same that we have in the start of this process, because we denote two classes of functions, m u theta and w theta u. After that, if we can formulate two theorems of Antipova in 2007. If function phi is from class M, then its Mellin transform exists and belongs to W. And the following formula is valid. Okay, if we use direct and then inverse Mellin transform, that we get same function. And another theorem is about another order of transformation. Start with inverse transform and then we use direct transform. And using first of this theorem, we can transform linearization of solution y mu into this formula. Okay, let's consider a system of algebraic equation. We consider a system of algebraic equation of form 2. Here, set lambda is a subset of integer relatives, and also denote lambda is the disjoint union of lambda drift. Because in different equations we may have same exponents lambda, we want that then in lambda we have different samples of this vector lambda small. Cardinality of lambda denotes n, and also the set lambda can be considered as n times big N matrix. Columns of this matrix are exponents lambda, and rows of this matrix we denote phi g. In following papers of Stepanenko and Antipova, to a monomial y in power mu of the principal solution y of the system, we put into correspondence the Mellin-Barnes integral of this form. Y vector gamma belongs polyhedron, and Q is a polynomial which can be represented as determinant. This integral can be obtained by formal calculation Mellin transform and then in inverse Mellin transform. But in this case we don't sure that the conditions of theorem of Antipova are satisfied. Thank you. But we can get this formal integral. Let's show two facts which we use in our paper. For general Mellin-Barnes integral phi at z, this form denotes the function g. This function is a partially linear function which defined by arguments of gamma functions in this integral. Rg is this Rg, bk is this bk. For any integration set gamma outside polar set of convergence, outside polar set of gamma functions in numerator, the convergence domain of Mellin-Barnes integral is equal to preimage of domain U, this domain preimage of mapping argument. If we have Cn n, which is corresponding to point R. That first, etc. R. Zn. And we have domain in Rn, and then we have the preimage in Cn, complex variable. If the set U is not empty, it coincides with the interior of the polyhedron theta, where vectors plus minus v1, etc., vd are all unit vectors that generate the fund k, defined by the partition of Rm by hyperplanes Ag and bk. It's Ag and bk, which we see here. And second fact that we use is the theorem about a partition theorem of Euclidean n-space. Let Vn be an n-dimensional vector space over the rails. Let psi1, psi n, and eta1, eta n be two n vectors in Vn, such that every sequence of vectors alpha 1, alpha n, where alpha e is psi y or eta I is linear dependent set. Let alpha 1 and alpha n in angle brackets denote the column spanned by these alphas. In other words, it's the set of all linear combinations of the alpha with non-negative coefficients. The 2 in power n columns in Vn spanned by 2 in power n such sequence alphas will be said to partition Vn if their union is all V, and if intersection of every pair these columns are column of lower dimension spanned by the common vectors in these sets. We may and shall assume that Vn is the usual Euclidean space. Let the orientation of n-ordered sets vectors alpha 1, alpha n be given by, as usual, by the sign of determinant. Any n-1 of alpha determine a hyperplane separating En into two half spaces lying on opposite sides of hyperplane. For the sake of simplicity in the statement of the theorem, we assume without loss of generality that first set of vectors, psi1, psi1 is positive oriented. The 2 in power n columns alphas spanned by alphas partition En if and only if sign of determinant alpha 1, alpha n is equal minus 1 in power s, where s is the number of etas among the alphas. Equivalently, if and only if with respect to every choice of n-1 alphas, the xi and eta for the omitted index are separated by the hyperplane determined by these alphas. And then consider the matrices of the form 6. This matrix is composed by exponents of the monomials in the system 2, where each column is a vector lambda j from big lambda j. The first column is the exponent of some monomial in first equation, the second column is the monomial of the second equation, etc. We call a minor of the matrix principal if the indices of chosen columns coincide with indices of chosen rows. In these terms, we can formulate this theorem. Integral 3 corresponding to a principal solution of a system of algebraic equations 2 has a non-empty domain of convergence if and only if in each matrix of the form 6 all principal minors are positive. And moreover, we have a consequence from linear algebra. This form, let R is non-negative n times n matrix and A, E, B its rows. Consider the function G A of this form. It's also partially linear function. And all principal minors of A are positive if and only if the function G is positive for V non equals 0. That's all. Thank you for attention.
Thanks. Danke the speakers for interesting